You now understand what it's like to do some AI. You can do some AI when you build a rule-based expert system to capture the behavior of novices in a field, and you can build systems that do various kinds of searches, and you can talk endlessly about constraint propagation and its virtue in cutting a horribly exponential problem down to practicable computation. So that's half the story about basic AI. There are other paradigms. We talked about the generate and test paradigm, right? That's a 5-minute thing, but now it's part of your vocabulary. How many of these are there? Maybe half a dozen more have found actual use. Some of these paradigms are paradigms you would have to work at for a month to understand, and in the end they have a grand total of exactly one application. A good example of that is use of formal logic in AI. A lot of people worked on that. It can get mathematically as hairy as you like. And for many years I despaired of anybody ever finding a practical application for it. And then one day a good friend of mine discovered that it was exactly the right tool for building systems that diagnose and work around failures on spacecraft. Terrific application. So every once in a while you get surprised by that. But on the other hand, in terms of cost effectiveness, it's rarely the case you want to spend a month or a year tooling up on a paradigm that in the end seems to have limited application. So we picked rule-based expert systems and search and constraint checking as examples of stuff that's had widespread use, stuff that you are guaranteed to find useful downstream. And we're going to do the same thing today. I want to talk about technology that is guaranteed to be useful because it's been useful thousands of times, even thousands of times before anybody even coined the term artificial intelligence. See, artificial intelligence is a slippery subject, and if you try to find a fence that you can put around AI, you can't do it. It's more of a direction or an attitude in many cases than a prescribed body of techniques. So some of the stuff we borrow and steal from other disciplines, and in particular, one of the things that we stole from another discipline is the notion of nearest neighbor learning, which was one of the two things that we'll talk about today. But before I get into that too much detail, maybe I better draw a little diagram here to give you a little bit of a context for understanding, for thinking about the stuff we're going to talk about today. If you think about how AI folks do learning, or how learning is done in general, let's say, you can divide the world roughly into two pieces. One piece is reasoning based, and the other is regularity based. And this is what we do, and this is what AI does. We do some of this too, no doubt about it. But techniques over on the reasoning side, like learning about what an arch is, have had limited practical application. Most of the practical application has come out of regularity-based learning. But of course, us AI guys are not the only practitioners of that. We've got the statisticians and the theoreticians. Theoreticians in computer science and elsewhere. Under the AI heading, we have a variety of techniques like nearest neighbors, identification trees, neural nets, sad to say it's also an NN, genetic algorithms, and others. And there's a tendency for these things to become mathematical and ultimately end up in the hands of statisticians and theoreticians who love to prove theorems about those things. So those things can look from a distance as horribly mathematical subjects. But in the end, there's some simple intuitions that allow us to deploy that stuff without spending 10 years reading the literature. And that's what we're going to talk about. particular, I want to introduce the idea of nearest neighbors today and identification trees. And then we'll talk about some of these other things tomorrow. Who knows how many nearest neighbor systems have been built? These systems were first built by people who styled themselves as pattern recognition people. And these pattern recognition techniques have been borrowed and stolen and absorbed into AI because they were the right mechanisms for solving certain problems. The way all that works is conceptually is you have some kind of sensors, some kind of sensor or sensors, and they produce features. And these features are fed into some sort of recognition engine. And out comes an identification. So that's pretty abstract, and I'd like to bring it right down to an example. And the example is over here on a display, where I have dug into my electrical box at home and fished up a bunch of electrical covers. So we can imagine a robot might be interested in sorting these as they come down the line. I can't imagine such a, well, suspending disbelief, we can imagine such a robot. So how would a robot go about recognizing which cover is which? Well, presumably its eye would generate some features. And one feature might be the total area of the cover. Another might be the whole area, the area of the whole. Not the W-H-O-L, but the whole area. And these things seem to come in two sizes, big and little. And the maximum amount of hole area would be four of those, four socket holes. So over there on the projector, I've got the biggest possible cover with the maximum number of holes. So we'll say that that particular cover, we'll call it number 1, ends up here in this so-called feature space. There are two features, whole area and area. And this particular cover ends up at that particular position. Now sorting through here, there's another one with half as much total area and half as much whole area. So that would be, let's call that number 2. So that's half of each. Must go right there. Then we got one which is a blank and it has no holes at all as the maximum area. We'll call that number 3. And now we have one that's maximum size, but it's a switch cover, so the whole area is somewhat smaller. So that's maximum size, and we'll say that the whole area is right about there. Then we got one that's got half of both, so we'll call it number 5. So those are the Platonic ideals. Those are the places in an idealized space where those switch cover, sorry, those electrical box covers would end up. But now nothing's perfect, and so when the eye reports on a particular cover, it's not going to end up exactly at one of these places, but it might end up here. So obviously, this looks like it's a 2, because that's the closest one. Hence the sobriquet. Okay, nearest neighbors. So if you then say that you'll identify these covers according to which of these idealized covers they end up being closest to, you're making a statement about how you're dividing up this space. And in particular, if I can draw myself some guidelines, you're going to be dividing the space up like that. Those are the boundary lines between these idealized positions. So anything in here would be recognized as a 4. Easy idea. Sometimes it's an easy idea that is implemented in a way that disguises the easiness behind it. I'd like to give you one example that's relevant to the project assignment. Let's say that we're not dealing with electrical box covers, but we're dealing with magazine articles. And we want to categorize them because somehow somebody didn't go to Ars Digita and made a file without keeping track of which magazine the articles came from. So it's our task to separate the articles into 2 piles. One set of articles come from Wired magazine, and the other set of articles come from Town and Country magazine. As you know, Wired is kind of a hacker's magazine, and Town and Country is a very genteel magazine for rich people who live in the suburbs. Okay? So right away we say, well, let's see. We imagine that the Wired magazine articles are going to use the word computer a lot. And maybe even the word hacking. Oops, let's put that down here. So we're just going to count the number of words. Count the number of times hacking occurs in an article, and count the number of times computer. The word computer occurs in an article. So you would imagine that articles from Wired magazine, you know, they'd be all over the place like so. And what about articles from Town and Country? Well, they ride horses a lot, and for them the idea of hacking has a slightly different meaning. Okay? So they're likely to have some articles that might end up here. Every once in a while they'll talk about computer stocks, I guess, so they'll end up there. So how would we divide these articles up according to which magazine they likely come from? Well, we can use the nearest neighbor idea. This is a feature space. It's a space of how many times hacking occurs and how many times computer occurs. Trouble is, this article must have been very short, and it's pretty close to one of those hacking articles. So the idea of using nearest neighbor here, categorizing an article according to these known samples, might at first cause you some pause because it looks like there might be some confusion. How can we help this algorithm? How can we help out here? The nature of the space doesn't seem to lend itself to nearest neighbors. Any suggestions?
Well, if that's really the issue, we can normalize it based on length.
You can normalize based on length. Any other suggestions? That might be right, I'm not sure.
Add a few more words and then just computer hacking. That's possible.
Well, let me give you some. I'm not sure what you meant by that, but.
Another dimension.
What?
Another dimension.
Another dimension might help. Yeah.
That's what the other word.
You might try all the words. You might try all the words and then get rid of the function words like the and By the way, you might be surprised to know how much of the space of English writing is occupied by the frequent words. I got curious about that one day and ran a little program over one of my textbooks and discovered that 10 words account for 25% of the words I use. So maybe a monkey could do it. But you know, maybe the problem is that we're using the wrong distance measurement. We're thinking of Euclidean distance here in this space. And we could normalize it so that, you know, there's the same spread in both dimensions or something. But there's another idea about that's focused on the dimension idea, and that is we can change the distance metric. We can change what it means to be close to something. So is that enough of a hint? Can you sort of get it now? See what's happening here? All the Wired magazine articles are off in that direction, and all the Town and Country articles are off in that direction. So let's just emphasize that a little bit by drawing vectors from the origin to each of those places in this space. And now you can see that there's no problem at all. So in fact, until recently, this was more or less the exclusive way that people did article classification and information retrieval. How do you do information retrieval here? Well, you say, I would like an article that talks about hacking computers, and what you supply is a very short vector in that direction, just one word each, right? I want an article that talks about hacking computers. There's one hacking and one computer. It's in that direction. So it's a lot shorter than the vectors that count up all the words in the articles, but it's in the same direction. So you can use this either for classification or for information retrieval. And like all ideas that are intuitively appealing, you can now build a whole career on top of this with with variations and sophistications of various sorts. But that's the fundamental idea. And if that's all you do, you can do pretty well. You get to a point of diminishing returns as you add these layer and layer of hacks. You can do pretty well with this. You get rid of the function words, you can do even better. And you think about it a little harder, and you can do better still. And pretty soon, you're not doing as well as the pros, but you're pretty close. How can you do better? Well, today you might do better by actually analyzing the language, by actually doing some parsing and writing programs that consider the relations amongst the words, not just the word counts. And if you do that, then you have some hope of distinguishing between man bites dog and dog bites man, which have the same words in them. But this works pretty well, and it's a good example of how you can rapidly put together a system based on nearest neighbors that does something useful.
You could bring in statisticians too.
You could bring in statisticians too, who are the custodians of a certain kind of knowledge that's applicable to this sort of hacking. In fact, there must be libraries full of statistical papers in statistical oriented journals talking about multivariate normal distributions and this and that, and elongated distributions and distributions of unequal size. And this stuff can get pretty hairy if you want to go mathematical, no doubt about it. And you get some utility from that. But the intuition is the same. Just pick the thing that's close. But close means a couple of different things, and maybe we should spend just a minute bringing that up. Close here in this electrical cover thing means that you've got some covers, and there's going to be some manufacturing variation and some variation in your sensors that displace an observed set of features from the ideal set of features. So what you're doing is you're using the features to recognize what category you're in. There are other cases in which you're using some features to predict other features. And it looks the same, but it's a different point. Suppose, for instance, you were interested in using data to predict when a user of a credit card is likely to go bankrupt. What credit card companies like to do is they like to run you right up to the limit, keep you there for the rest of your life. But they don't like it when you go bankrupt. So they would like to be able to predict that. An example of a questionable use of computer science, but it's a good illustration nevertheless. So you might say, well, let's see, let's measure the relative frequency of use on weekends. Let's measure the number of times the credit card is used in a gambling establishment. Let's measure the number of times the credit card is used in a bar. Let's measure the number of times that the credit card is used in a basic clothing store, to pay church dues. I don't know, you can imagine a bunch of features, and then try to use that to predict bankruptcy. So it's the idea that if things are similar in some ways, they're likely to be similar in other ways. So you can use nearest neighbors that way too. It's a little bit different twist. You know, you'd be surprised. This sort of nearest neighbor idea has even proved to be, to everyone's astonishment, the best way to control a robot arm. How can you control a robot arm this way? Well, the trouble with a robot or a human is that we have all these degrees of freedom and all the torques that can be applied to the joints by way of our muscles. So you can certainly build a giant table that contains positions, velocities, accelerations, and torques. And Newton tells us that these are related. In fact, if you know these three, you can determine the torque. If you know these three, if you know these two and the torque, you can determine the acceleration. So you can take a robot principle through a childhood in which you just have it wave its arm randomly. And for each little piece of motion, each little increment of movement, you write something in this table. A relationship between the known position, the known velocity, the known acceleration, and the torque when that motion takes place. All right? So now if I want to get a robot to throw something, all I need to do is divide it up into short little pieces and look up the torques in the table. Now which torque do I get? Well, the one that's nearest to that combination of position, velocity, and acceleration through which I want the arm to go when I'm throwing. Now, for a long time, it looked like that was a ridiculous way to do it because when it was first thought up, there was no hope that a computer could be fast enough or have enough memory to do the job. So people spent 15 years doing hairy mathematics as a result, and then they woke up 15 years later and said, wait a minute, computers are fast enough, they do have enough memory. And even better still, you can introduce the notion of practice. Because if I want to do this motion, as I often do, reach for a coffee cup, and I've got a table of things that I learned from childhood, I might come wobbling in the first time, but now I'm still writing into my table. And the things that I'm writing into my table are pretty close to this trajectory that I'm trying to move along. So you get the notion of practice. Now when you do an interpolation amongst a few points in the vicinity of the motion, you got good points to interpolate among, and pretty soon, within a few tries, you're going in like an Olympic athlete. Some people think this is the way we do it. Cerebellum looks like a pretty good lookup table. Is there enough memory in the cerebellum? Well, being computer scientists, we got to really work out the numbers. So, suppose you want a robot to become a good baseball pitcher. Red Sox could use another Pedro Martinez. So you might say, well, let's see, we'll build a robot that looks just like Pedro, and we'll watch Pedro in action for a while, put some sensors on it so we can get the muscle torques, and then we'll just write down everything. And so the question is, how much would you have to write down? Well, let's see, you might divide the pitching motion into 100 segments. And maybe you need to record information about those 100 segments. Maybe there are 100 muscles. 100 muscles and joints you need to keep track of. And for each of those, maybe you want to record 100 bytes. Then on any given day, Pedro probably throws something in the vicinity of 100 pitches.
Between 90 and 100, that is the act.
But there's warm-up and everything, so maybe it's... And then how many days a year does he pitch? I don't know, not more than 100. Maybe he does winter ball too, who knows. And how long does he, how long is his career? We'll say 100 years. So that's 2, 4, 6, 8, 10, 12. So that's, we need 10 to the 12 bytes, even being very generous and not doing any redundancy reduction or anything like that. Is that a number we can manage? Can we get it on a disk? You can get it on a disk. What's a big PC disk these days? 30 gigabytes? How many? 100 gigabytes?
8.
Well, that's all we need, right? PC disk. How about the cerebellum? Does anybody know how many neurons there are in the brain? I used to take a neuroanatomy from a wonderful professor at MIT named Wally Nauta. Came from Holland. And he used to say there are 10 to the 10th neurons in the brain, of which 10 to the 11th are in the cerebellum alone. It was his way of saying that the cerebellum is unbelievably rich in neurons. And not only neurons, but in connections. There might be 100,000 synapses for each of those. So that's 10 to the 16th. So if you drink wine and wax eloquent and don't think too scholarly or anything like that, you can easily imagine that the cerebellum is a table that can handle the sort of information you need in order to do motion. So that's nearest neighbors. There it is in the simple. These electrical covers introduce the idea of a feature space, a division of this feature space according to who's nearest to what. Some thoughts about what it means to be near. It can mean either that you belong to the same category or maybe predictive, as in the bankruptcy case. Sometimes the distance metric is a little unusual, not the ordinary metric you would find in the Euclidean space. And sometimes you find the same idea used in a very exotic context like robotic arm control. So it's a very useful idea. Not one invented by AI people. This existed long before AI was conceived. But it's often used by people who style themselves as practitioners of AI. But having said all that, there are one or two problems with it that caused AI practitioners to invent the idea of identification tree, which, by the way, again runs parallel to stuff that's been done before and after in statistics. But I'm going to give you the AI practitioner's version of this idea. Why was the idea developed? Well, it's developed because there's some problems here, at least on the surface. One is that you may have a lot of features that can be computed but are very expensive to compute or very time-consuming to compute. And so you won't want to compute them unless you have to. That's reason number one. Reason number one is that you would like to organize your test computation so that the expensive tests aren't used unless they're necessary. No test is used unless it's necessary. No test is used unless it's useful. So that's one point. Another point is that many of the tests that you might use are either redundant with a test you've already got or not relevant at all. If two tests do the same thing, then counting both is essentially counting the test double. If a test is not, if a feature computation is not relevant at all, it can throw off your answer by accidental nearnesses. So that's number two. You would like a mechanism that distinguishes between the tests that are really useful and the tests that aren't. Reason number three is that sometimes you have to work with categorical rather than numerical data. You might have to work with red, green, and blue, the names, instead of something that produces a number for you. Now, in a red, blue, green, and blue case, you say, well, okay, I'll just convert that to the spectrum, to the wavelength of the light, and so sometimes you can convert categorical data into numerical data and get it into this format. But sometimes you can't, or at least can't conveniently, or at least can't in a way that isn't really tricking your system into doing something it doesn't feel good about doing. So if it matters, if occupation matters, that's pretty hard to put into a numerical category. Maybe you can do it, but it's not going to feel good. Accordingly, the idea of the identification tree was developed. And what I'm going to do to introduce this, the same thing you now see I'm in the habit of doing. I'll tell you about a couple of important applications to make it real, but I'll demonstrate in some little toy world that exposes the idea easily. So it's not hard to pick a couple of applications in which this idea has been used, because it's been used thousands of times. Thousands of times. One of the early applications was done by Ross Quinlan, an Australian scientist who is largely responsible for promoting this idea inside of artificial intelligence and doing the original work on it. Ross did it with thyroid data in one of his demonstrations. You have all sorts of tests, and you want to know what kind of thyroid disease the patient has. So he was able to show how his technology could be used to do this test, and if it turns out this way, you do another test. If it goes the other way, you do a different test. Down at the bottom, you say, oh, this is hypothyroidism. And did a great job. Another one which I put in my book as an example is a situation in which a nuclear power fuel production factory was trying to increase yield. And by looking at that problem in just the right way, it turned out to be a recognition problem. Which features driven which way will produce the highest yield? Well, to solve that question, they had to look at the data that they had from the past and say, oh, I see. I can recognize that the yield will be good if I see a certain combination of feature sets. But some of the features they had turned out to be irrelevant. Some of the things that they were planning to really crank down on and hold more constant were not actually relevant to yield. And other parameters, other pressures and temperatures and whatnot that they hadn't suspected mattered turned out to be the critical ones. And so the payback period in that little enterprise was about 2 hours. And, the increased yield over 2 hours of time was enough to pay for the whole enterprise of buying the system, paying the hackers and everything else. So sometimes you get a very high leverage situations like that. But what is the idea? Well, here's the toy example. Are any of you from Eastern Europe? No? We have a lot of Eastern Europeans now at MIT ever since the end of the Cold War. And we, of course, welcome them to our bosom. At the same time, we have some concerns because we know that that's where vampires come from. And, you want to be real careful not to get too close to a vampire. So you might think, well, you can perform some tests. And from those tests, you might hope to develop a program that can recognize vampire tendencies. So here's some tests. Now, you don't know just exactly which of those tests are really relevant, and you don't want to condemn someone without evidence. So what we're going to do is we're going to develop a identification tree that will use these tests to determine whether somebody's a vampire. And we'll use this sample database as our training data, because we know which of these people are vampires. Now, having done all this, I have to say one thing here with emphasis, and that is that nobody would reach any conclusions on the basis of 8 samples on anything, right? Because there's only one example of certain cases. So what you have to do to imagine this is realistic is suppose that you took this data and multiplied it times 100 times. For each record here, you have 100 records in this larger database. If you had that database, then you could imagine that there was something to it. But I want to develop the solution to this problem right here, so I'm going to work with a database of 8 samples, just by way of illustration. So how are we going to do this? Well, first we're going to test for this, and then depending on the outcome, we're going to test for that, and pretty soon we'll have a zeroed in on whether a person is or is not a vampire. But some tests will be, some combinations will result in a big tree, like maybe that one, and others will develop a smaller tree, like that one. So which tree would we like to develop? Well, we'd like to develop the small one. Is that because small is good? No, it's because small is Occam's razor. What we're going to try to do here is come up with the simplest explanation that covers the data, on the theory that the simplest explanation is the one that's most likely to have predictive value. So basically what we're going to do is we're going to arrange the test, whether there's a shadow or no shadow and so on. We're going to arrange the test so as to build a small tree with the sample data, not a big tree with the sample data. And then we will believe that that small tree has predictive value. So that's the intuition. But now, you're a computer scientist, so first thing you want to ask is, well, why build the tree? Why not just try them all? That's NP. Too much computation. So you have to have some heuristic mechanism for building a tree that is likely to be small. But it's true that a program that tried everything might find one that's even smaller, and in certain screw cases. So we've got to use heuristic methods because the problem is computationally intractable without them. So what to do? Well, first we have 4 tests. Shadow or not. And we have garlic or not. And we have accent. And we have complexion. Now with a shadow, sometimes you can't tell because a lot of students don't go out at night or during the daytime, so you can't tell if they cast a shadow or not. But sometimes they do, and sometimes they don't, by observation. They either eat garlic, they've either been observed to eat garlic, or not observed to eat garlic. As far as their accent, it can be heavy, odd, or none. Maybe that's important. But on the other hand, a lot of vampires are very concerned about their accent and manage to, if you're a Dracula, they worked hard on getting rid of the accent. And the complexion can be pale, ruddy, or average, I guess. So all I've done is drawn out, for our easy inspection, all of the tests that can be applied. And now what I want to do is I want to run a sample data set through all of them. So garlic is easy. There are 3 yeses for garlic, and all 3 produce a no, not a vampire. I guess, let's see, 3 yeses and all those. There are 3 vampires out of 8. So over here we must have plus, 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 minus, minus. You'll have to check me with this data because it's hard to get it all right on my feet. But I think that's right for garlic. Let's do the same thing quickly for the others. Does the individual cast a shadow? Well, there are 4 cases where we don't know. 2 yeses and 2 nos. If the individual does cast a shadow, then it's not a vampire. So far we've got, and then if it's no, it doesn't cast a shadow, yep, it's a vampire. 4, that's 8. Okay. Let's check out the accent. In three cases, there's no accent. No, no, yes. If the accent is odd, there's a yes and a no. And if the accent is heavy, there are three cases: yes, no, no. Finally, complexion. If the individual is pale, two pales, what? Two no's. How about ready? Two no's and a yes. Average?
Or two yeses and a no.
And quick scan, they all work out. So which is the test that we should use first?
Garlic.
So one suggestion is garlic. Why do you think?
If you know someone's eating garlic, you can discount them.
Ah, he's using logic. Shame. Shame. It's the wrong branch. You're reasoning. You know, and it brings up a good point, because these methods that we're talking about don't use reasoning. And as a consequence, they can reach screwy conclusions. I like to point out that if a Martian came, well, if a dog or a cat or a Martian looked at the question of looked at drinking diet drinks, they would quickly conclude that diet drinks make people fat, because they would see a correlation between the diet drinks and fat people. On the other hand, we know that that's not the way it goes. It's people drink diet drinks because they don't want to be fat. In the end, dogs and cats and Martians might be right, because some people say that aspartame increases appetite, but that's another question. These things don't know anything, and accordingly can find correlations that are not causal in connection. They might stem from a common cause, but that's not the point. What we're looking for is regularity. So there are lots of ways we could decide which is the best test. A way that produces garlic as the best answer can be found. But what I want to do is I'm going to use for sake of illustration, a sort of classroom way, and then I'll talk about the real way. So the classroom way is to say a test is good if it tends to divide the sample set into homogeneous categories. So this test takes the 8 individuals that are in the sample set and puts 4 of them in homogeneous categories. And it puts 4 of them in a mixed category. So let's give it a score of 4. The garlic test, alas, only does 3. The accent test is horrible. It gives us a 0. And the complexion test gives us a 2. So if we say we're going to be able to build a small tree, if we choose tests that tend to divide things into homogeneous categories, then we'll pick shadow as our first test. So let's start up our decision tree over here then with the shadow test. Question mark? Yes? No. Plus, minus, minus, minus. And now we got a mixed result coming out of that third branch. So we have to decide what tests to apply here in order to divide the 4 samples into homogeneous sets. So what are we going to do? Well, we're going to do the same thing we did to pick the first test. Only now we're only going to consider the 4 individuals that actually reach that particular point in our evolving identification tree. Right? So instead of dividing 8 samples amongst the branches, we're just going to divide the 4 samples that come out of here. So what I've done is I've just crossed out all of the samples for which the shadow test produces something other than a question mark. So there are 4 remaining. So now let's go back and do the same thing. Do the same thing again. Well, we don't have to do the shadow test because we've already milked that dry. We've made that our first choice. So what about the garlic test? Okay, so can somebody help me out with that? Of the 4 remaining samples, 2 are yes and 2 are no. The yeses are both no, and the no's are both yes. How about the accent test? Let's just do this mindlessly and then we'll think about it. The accent test, of the remaining 4, 2 are none and 2 are odd. The 2 nones are no and yes. 2 odds are no and yes. And what else will we have? Pardon? Where? For none. No and yes. Right? And then for complexion, 1 pale, that's a no. 1 ruddy, that's yes. 2 ruddies? I'm sorry, there's a yes and another ruddy is a no. And then for average, then we must have a yes. So now we're keeping score by adding up the number of things that have been placed in homogeneous categories. So there are 4 here, 2 here, and 0 here. A clear winner has emerged. Looks like the garlic test is the right thing to do next. And sure enough, if we add that to our identification tree, yes eats garlic, no does not, then we get minus, minus, plus, plus. Which is satisfying. I mean, we can, if we want to know if somebody's a garlic, somebody's a vampire or not, we see if they cast a shadow, and if they do, they're not a vampire. We know that. If we can't tell, then we might see if they eat garlic or avoid it, and if they eat garlic, then they're not a vampire. So it looks like from our sample data set, the accent and complexion features are not particularly useful. So we wouldn't want to bother to go to the expense of computing them. It might be that they would be slightly useful if we didn't have these tests, or it might be that they're completely irrelevant. I don't know. I haven't tried. I haven't worked it out. So that's the idea of identification tree. You build a tree that tries to take the sample set and get as quickly as possible to homogeneous, gets as quickly as possible to a situation in which the samples are in homogeneous sets at the bottom of the tree. But it's a classroom method of doing disorder analysis. We just pick the test that puts the most things in homogeneous sets. If you have a big data set, nothing's going to be in a homogeneous set. No test will produce anything in a homogeneous set because there'll be errors and because it's too hard and this and that. So this won't work on real. This method, the intuition still works, but the method doesn't. So what to do? We have to find a new way to measure disorder. And who are the custodians of mechanisms for measuring disorder? Statisticians. Who else? Thermodynamicists. Who else? Something that's dear to our heart is computer scientists. Who measures disorder? Information theorists. They are the sine qua non of information, of disorder measurement. So if you ask an information theorist to tell you what the disorder is in a set consisting of 3 pluses and 2 minuses, they will tell you. And what will they tell you? Well, they will count the number of bits in it. And how do they do that? They'll use a formula. They have a formula for measuring disorder. So we're going to look at that formula. Not because it's sacred, because it isn't. It's more sacred to information theorists than it is to us, because the formula has certain properties that make information theory work. But for us, it's just one of many possible functions for measuring disorder. Happens to be very convenient. But here's what it would look like. We're going to say that the disorder and I might call it entropy or something, but I like to call it disorder because that's what we're interested in here, is deciding how disordered a set is. The disorder is equal to minus the number of positives over the total number times the log to the base 2 of the positives over the total number minus the negatives over the total number log 2 of the negatives over the total number. Now, we don't want to do too much with that except make sure it makes sense. Let's graph it as a function of p over t. So we go from 0 to 1. Can't have more positives than the total number, after all. And we don't know where it's going to max out yet, but it's going to max out somewhere. Now, let's suppose that we've got a situation in which the number of positives and the number of negatives is balanced. So that means p over t is 1/2, right? So what's the formula give us for that condition? Well, it's minus 1/2 times log to the base 2 of 1/2, and that's symmetric. So we'll just multiply that times 2. So what's the logarithm of 1/2? It's the same as minus the logarithm of 2. And minus the logarithm of 2 must be minus 1. So, oh, guess what it is? It's 1. So we got 1 point on our curve. Right there. Now the slightly more complicated case, what if the number of positives is 0? So everybody's a negative. Well, in that case, we have 0 minus 0 times the log 2 of 0 minus 1 log 2 of 1. What's the logarithm to the base 2 of 1? 0, because 2 to the 0 is 1. So we get 0 from this side. And what's 0 log 0? Well, 0 is 0, and log 0 is choke, minus infinity. So to figure that out, we got to reach back into elementary calculus and say, that's the first time and only time in our life we'll ever apply L'Hopital's rule, and figure out that limit. And it turns out that that limit is not minus infinity; it's 0. So now we have another point on our curve, and by symmetry, we have 3 points on our curve. And if we did a few more points, we'd discover that the curve looks like that. So that's a great little function. It's maximum when things are perfectly balanced, and it's 0 when things are perfectly homogeneous. So we could go over here and say, well, the disorder of this guy is 1, the disorder of this guy is 0, and the disorder of this guy is 0. So if we weight that by the number of samples that go down the branches, we can say, well, half the samples go down here, 3/8 go here, and 1/8 go here. So the average disorder produced by this test is 0.5. And we could do the same thing for the other tests. And what we would discover is that the numbers, we need a calculator or a little program to compute the numbers for these other three, but they're going to be greater than 0.5. So we get the same result if we use the official mechanism with an information theoretic measure of disorder as we got from our kind of classroom exercise of just looking at how many things ended up in homogeneous sets. And that's all there is to that, except for a couple of flourishes. But there you have it. There's the idea, the reason for the idea, and now a couple of flourishes. Flourish number 1 is, how does this divide up the sample space? Well, wait a minute. These things here are all categorical features, not numerical features. So how do we can't even talk about dividing up a space because the space is categorical. And worse yet, how do we use a method like this on thyroid data where all those tests coming out of the fancy machines are numeric instead of categorical? So once we've got this idea solidly understood from the point of view of what it's trying to do, build small trees, next thing we have to do is we have to generalize it to deal with numerical data. And that's easy, but you have to pay attention. This goes by quick, and if you blink at the wrong time, you'll miss it. So, well, let's see, a numerical test will produce samples that are along a line. And maybe we'll put some O's in here too, and imagine that our job is to find a test that separates the X's from the O's. Well, since this is numerical data, instead of saying, you know, does it belong to one category or another, we can say, is it or is it not a number bigger than some threshold? So our test will be greater than or less than t, this threshold value that I've put on the line. And so to use this mechanism then with numeric data, all I have to do is decide where the threshold should be. And that's my test. Pardon me?
Is there wizardry involved in determining where the threshold ought to be?
He says, is there wizardry involved in determining where the threshold ought to be? Yes, there's a little bit of wizardry. What we can do is we can say, for this particular threshold, what's the disorder measurement that it produces on the data set? So we can do the same thing we do with categorical data. But there's still a question of which threshold do we try? There's, after all, an infinite number of them. Maybe we could try the one that's in the middle. Or maybe we could try one that seems to be midway between the center of gravity of the x's and the zeros. There are lots of things we could do. But wait a minute, this is a computer. We don't care how much work it has to do. So we can try everything. Almost everything. What we end up actually doing is we say, let's try tests at the midpoint between every adjacent pair of samples. So if there are n samples, we'll try n. We'll consider that to define n-1 tests. Got that? So there are n samples. That defines, in general, n-1 tests that we can try. If we have several numerical measures, if we have m numerical measures, each of which has n samples, then we've got m times n-1 things to try. But it's a computer, and we don't care how much work it has to do when it sets up this problem. And that's how you handle numerical data. Okay, now once you got that, then there are a couple of observations you can make.
Do you keep these as separate tests in the
Yeah, yeah. But every time you pick a thing to put in your decision tree, you're picking a particular threshold. But now, a little further down in the tree, it may be the case that this test is useful again with a different threshold. So here, when we're doing categorical data, it never made sense to try shadow twice. But here with numerical data, it might make sense to use the thyroxine level twice with a different threshold. So now you know how to use this to deal with numerical data. And once you know how to deal with numerical data, then you can say how it divides up the feature space. So here's a way of dividing up the feature space. This way nearest neighbors divides up this feature space. But if we were going to use a decision tree on the same data set, what it would tell us is which test and which threshold for that test is the next one to be used. So if we were going to divide this into 5 categories using feature space data, it would give us a division that looks different. And I don't know how, well, we've only got one sample here, so it's not going to give us much of a challenge, but it might, for example, decide to use that test first with that threshold, and then it would use this one, and then it might use this one, and then it might use this one. So it divides up the space rectilinearly instead of, into these sort of, instead of in a, what you might think of as sort of honeycomb shape that the nearest neighbor kind of test does. One more flourish. can we relate any of this back to, Quinlan found that doctors have limited capacity to grasp graphical things. No offense. So, but what they can do is they can work with rules. So Quinlan decided it'd be nice if instead of showing somebody a tree, he showed them a set of rules that they could look at and say, yeah, that set of rules makes sense. So how can we go from the tree to rules? I don't know. Let me just try to write some things down. We know what it means to go down this branch. So if shadow equals question mark and garlic equals no, then vampire. Or to pick that branch, we could say if shadow equals no, then vampire. And now on a roll, if shadow equals yes, then not a vampire. And finally, if shadow equals question mark and garlic equals no, garlic equals yes, then innocent, not a vampire. So what can we say? Every path in an identification tree corresponds to a rule. And what Quinlan found with his medical experiments is that he could show endocrinologists the rules, and they would say, yeah, that make perfect sense. But they would never be able to pick exactly the right thresholds. That's a grunge work for a computer to do. But if you look at these rules, there's one more flourish you can do. We'll get off the end of these flourishes here in just 1 second. I think it's the last flourish. You can look at these rules and say, well, these rules are a byproduct of a process that divides up data. And up there at the early parts of the tree, things are going to be pretty arbitrary. So it may be that the rule set that's produced by this mechanism asks more questions than it really needs to. For example, we might look specifically at this rule here and ask ourselves the question, do we really need to determine what the outcome of the shadow situation is if we know that the individual eats garlic? You already said by logic that if it eats garlic, it's okay. But what we can do is we can just now go over this rule set with a process that tries out each of the clauses, the if parts, and says, do we make any mistakes if we leave it out? So if the individual eats garlic, yes, yes, and yes, we can see that the answer is always no. And we don't care whether the individual casts a shadow or not. So we can just get rid of that and simplify the rule set. So now we brought it all full circle, and this is, and when you add this final flourish, you have a perfectly reasonable way of attacking a data set with identification tree technology. And what do you get out of it? Well, you get out of it something that works, something that doesn't use a test if it's not relevant, something that lends itself to the production of rules that can be looked at and evaluated by an expert. So it's no wonder that this idea has been used tens of thousands of times. It's extremely useful. It's the first thing to try. If you don't know what you're doing, it's the first thing to try. How about, if it's numerical data, why not use nearest neighbors? Do this first and figure out what tests are relevant and then use nearest neighbors, maybe. But this is the first thing to try. Yes, Peter.
I've been sort of trying to map this onto multivariate techniques to classify things.
Yeah.
And what would happen if you had like two populations of vampires?
Yeah.
Some interaction, like shadow throwing, garlic loving, heavily accented, dark complected ones, and ones that didn't show have shadows, didn't eat garlic, didn't have accents, and light.
Right. Yeah.
You can generate the tree and have them at the bottom, but how does your sort of algorithm work? Because none of them partition things in ways that have more or less organization.
Well, I'm not sure exactly what your question is, but if your question is, can we handle more than two categories? The answer is sure.
Well, in interactions, I mean, where you would have, where none of those, shadow, garlic, accent, would divide them at all.
Yeah, but it's the combination that does the division.
Right.
So because it's a combination that does division, and because this kind of lines up a sequence of tests that's splitting the space, you're hoping that you can eventually divide things up into your multiple kinds of vampires. But remember, all these techniques are doing, I keep coming back to the idea of representation. And the representation under both nearest neighbors and most of identification tree technology is the feature space. So really what we're talking about is just different ways of dividing up the feature space. What we're depending on is that like things will cluster together. So this might be not different kinds of electrical covers, but might be different kinds of vampires that all cluster together in various ways. So sure, you can organize a system of tests that will zero in on a division of the space that properly separates those. Having said all that there's not a problem. Some techniques like to divide things into yes and no. Not this one, but some techniques like to divide things into yes and no. So with those techniques, a thing that's often done is to say, well, for each of my categories, I'll do a separate tree. And then once I've used the separate tree, then I'll combine that data to figure out what's really going on. So that's identification trees. Now this stuff has analogs and statistics. The statisticians do it more mathematically. This is easy to understand. It's intuitive. But it doesn't have much of a feel. From a distance, it doesn't have much of an AI feel. It's not inspired by biology. It's not inspired by evolution. So you might think then that there would be other techniques that would be more AI-like. Well, as practical computer science, we don't care where the solution comes from. It could come from a Ouija board as long as it works, right? But on the other hand, you can't really talk about AI at a cocktail party without being conversant in the lingo of neural nets and genetic algorithms. And that's why tomorrow what we'll do is we'll focus on those alternative approaches to learning and see if we can relate those back to the question that we've talked about today, which is namely, how does the technique divide up the space? And does it do a good job of dividing up the space, or is it a force fit? So that's where we're heading next time. Okay, I think that's all for this morning.